Charles and Philip mentioned that there was some confusion about how to have the 328 and the accelerometer communicate. I covered that stuff in lecture, but I went through it pretty fast, so I was planning on going back over that again today, a little bit revisiting that stuff, just so everyone's on the same page. There's two parts to this. There's the idea that we need to be notified when there's new samples read from the accelerometer because it's recording acceleration data at, I forget what the speed is, but it's significantly slower than the clock rate of the processor. So we need a way for it to tell us when there's new readings for the processor to consume. So you can either use an external interrupt for that, or you can use polling. And then the SPI communication, there's a few things that you have to be comfortable with here. First, the idea of SPI in general, in that there's a master and a slave, where in this case the 328 is the master, the accelerometer is the slave, and every time you do an SPI transaction, you're actually exchanging a byte. So you're sending, the master sending a byte to the slave sending a byte to the master, and the accelerometer defines its own protocol that sits on top of the SPI, which is this idea where you can do a read or a write operation initiated by the master, by the processor. But the problem is that has to be hacked a little bit to work with SPI. So the way they do it is they have to do at least 2 SPI transactions to do a read or a write. So if you want to read, you have to have the master has to send the address to the accelerometer. The accelerometer cannot send the value being read back at the same time because it has to wait until it has the whole address before it can do that. So the data that you get back from the accelerometer is garbage. I don't. If any of you looked at what that is, I don't know what it sends back, but whatever it sends back, you just ignore, right? I'm actually kind of curious what it sends now. But it sent, so as the master, you send it an address along with 2 control bits to tell it whether you're reading or writing and whether you're doing a burst read or write. And then while you're doing that, the accelerometer is sending something back. I don't know what it is, but you ignore that. And then you have to follow that up with a second SPI exchange. So if you're doing a read, the master would then send garbage to the accelerometer would send back the contents of the address that was being requested in the first transaction, right? And if you're doing a write, then the master sends the data it's writing in the second transaction, and the slave sends back something. I don't know. Don't know what it sends back, but you ignore it, whatever it is, right? It'd be funny if it put if it put something in there, like an Easter egg, right? Okay, so what's the point? You have to know a little bit about SPI to use SPI. Even though SPI is being physically implemented in hardware, you have to understand what's going on in order to use even the hardware, right? You have to understand the notion that there's this slave select and that there's an exchange happening. And then on top of that, you have to understand the specific protocol that the LIS3, is that what it's called? LIS3 is expecting, right? Okay, so first of all, let me step back here a minute. What about this interrupt? Are any of you trying to use the interrupt? So an interrupt is a signal that an external device sends that gets the attention of the processor, which means that if you have a laptop, every time you hit a key, an interrupt is fired, right? Every time a packet is received from the network destined for your computer, an interrupt is fired, right? And if I send your computer packets at a fast enough rate, it'll trigger interrupt so fast it'll live lock the machine. It's a denial of service attack, right? But that's a nice way of doing it because then the processor could be doing other things in the meantime. It doesn't have to keep, polling. In other words, keep asking over and over again in a loop if there's new data. So there are 2 external interrupt pins. that are called int0 and int1. I've put arrows to them. They overlap with PD2 and PD3. But how does that actually work? And this is something that I blew through this really fast last time I talked about it. I want to go into a little bit more details this time. So there's this interrupt pin, and it gets the attention of the processor, but how does it do that? Well, it could be, there's different ways this could work, and the interrupt pins are configurable on the chip. One way you can configure them is by making the interrupt indicate its intention to interrupt the processor by an edge, meaning a transition from low to high or high to low, right? So in this case, I've tried to depict this graphically. So PC stands for program counter. So the program counter will be executing code, and at some point the interrupt will go from low to high, so you have this rising edge, which will automatically make the program counter change to the interrupt service routine, interrupt service handler. Sorry, it should be ISR, not ISP. Sorry, that's my fault. Interrupt service routine, right? ISR. Now, the nice thing about the edge level, the edge sensitive, is that if the ISP finishes before the external device lowers the interrupt line, right? Or even, well, yeah, if it finishes before, in other words, I get done and I resume executing my code, I go back to what I was doing, right? That's okay, because eventually the interrupt line will have to drop, and the processor will ignore the falling edge. Likewise, it'll also ignore the fact that the interrupt request is still high even after it gets done with the interrupt service routine, right? That's the advantage of the edge sensitive. It can also be level sensitive, but you have to be careful there, because if you make it level sensitive, then the rising edge will still make the processor go into the interrupt service routine, but if the interrupt service routine finishes before the interrupt pin drops, then it will return to the code and then will automatically go back into the interrupt service routine again. It'll service this interrupt twice, right? Because it'll just see the level being high, and it'll think, oh, there's another interrupt being requested, right? So this is if I configure it to be level sensitive high, and this is if I configure it to be rising edge, right? Now, how you do this depends on how the external device works. So what are our options? Well, if you look at the EICRA, we have 4 options for how to recognize an interrupt, an external interrupt. Level sensitive on low. So whenever it's low, I consider that interrupt, which would be the opposite of what I showed here. This is a level sensitive high, right? You can make it level sensitive low. Any logical change, meaning a rising edge or a falling edge, can activate the interrupt. A falling edge or a rising edge. Now, this is weird because it's obviously missing this case. Level sensitive high, not supported. I don't know why. That seems odd. I think that would be an obvious one, but they don't support this mode actually. But they support the opposite, which would be the level sensitive it being low. Okay, and then there's also this mask register that you have to set if you want to enable the interrupt. So if you want to use the external interrupt in Lab 2, you have to set both of these registers, right? And of course you have to write the interrupt service routine. Okay. How do you do that? Well, it's just ISR, and with the vector name, you have to go inside this file to find the vector names, because for some reason they don't actually, as far as I know, there's nowhere that they list the interrupt vectors anywhere in the data sheet for the processor. You have to go into their code, their header file, to find that. And of course, also you have to make sure that the global interrupt enable is set as well. So in order for this to work, there's actually 4 things you have to do. You have to set the the type, how you want to recognize the interrupt, which is EICRA. You have to turn the mask on for the external interrupts, EIMSK. And in this case, if you're just using one of the interrupts, obviously you would just choose one or the other, like int 0, for instance. And then you have to write the service routine, and then you have to make sure that you enable all the interrupts, right, with the SEI function. Is that clear? Okay, so I showed an example of this in class, and again, I went through it really fast, so I just want to revisit here briefly. So I had this real simple example where I had a button where one side of the button was connected to pin 2, PD2, which is interrupt 0, and the other side was connected to, I guess, VDD. Right. So if you push the button, it would short the interrupt pin to VDD, right? And if you weren't pushing the button, the interrupt pin would be floating, wouldn't be connected to anything, right? And then I set up EICRA to be 1, 1, and this is how you specify binary in C, by the way. You put 0B as a prefix, and then 1, 1. That makes it a binary constant. 1, 1 corresponds to the rising edge. So then I enabled the interrupt 0 with EI mask, and I enabled global interrupts, and then I looked up in the header file, and I found out that the handler name is int0_vect, and then I wrote, it just prints pressed button, right? So whenever I push the button, it would print pressed button. Now I wasn't actually sure if this would work, because it's when you push the button, you're going to have a rising edge, but it's not going to go from ground to VDD. It's not going to go from 0 to 5 volts. It's going from floating. It's going from a disconnected state to 5 volts. But it still worked, right? Still worked. There's a better way I could have wired it up where if I wasn't pushing the button, it should have had a resistor to pull that down to ground. And then when I push the button, it would pull it up to 5 volts, but it still worked even in this case. So does that make sense? Okay. Next, SPI. Let's review that briefly. SPI is the 4 pins PB2 to PB5 is mapped to the 4 SPI pins. So you're going to have to wire these up to the board. It's shown how to do that too in the lab sheet for lab 2. So how do you use SPI? This is a kind of just a step-by-step guide on what to do. I think we also have this similar text also in the lab sheet. But basically, you want to set the SPI speed and the configuration parameters, CPOL, CFA, and the data order, the bit order, right? Whether you transmit the least significant bit first or the most significant bit first. And these are all specified in the SPI control register, SPCR. And then you have to set, this part kind of surprised me, but you have to set the SPI pins, you have to set the data direction register for those, right? I kind of thought that if you're using SPI, the hardware ought to override that anyway, but it doesn't. So you have to explicitly set up PB2, PB5, and PB3 as outputs in the DDRB register. Is it B? It's B, right? Yeah, B. And then you have to specify MISO as an input. Yeah, sorry, I have them here too. PB3, PB4, right? So that's the initialization. You could put that in your init function or at the beginning of main. And then whenever you want to use SPI, you have to set the SS pin to 0, the slave select. How do you do that? You treat it as if it were just a GPIO. Also surprised me because why is it that you have to, it's kind of a hybrid where you have to kind of treat it like a GPIO in the sense that you directly set some of the bits with your software, but then other bits like the S clock, for instance, are handled automatically for you, right? So it's kind of a hybrid hardware-software scheme. So you set that to 0, how? With port B, specifically pin 2 of port B, using the port B control register. You have to set that to 0. Does that start the SPI? Nope. Doesn't really do anything, actually. I don't know. I mean, it does a slave select. So it tells the accelerometer that you intend at some point in the future to talk to it, but nothing actually happens until you write to the SPDR, the SPI data register. Once you do that, it will shift the contents of that out to the peripheral, and it will activate the clock for you. So in other words, it will automatically drive MOSI and S clock, right? And then the peripheral will send data in on MISO. Make sense? Okay. And then you wait for the transmission. So you can either use an interrupt for this, or you can poll. And if you poll, polling requires that you check the SPIF bit and the SPI status register. So you keep waiting for that. What should you do? Should you interrupt or poll? I think in this case, you don't gain much from using an interrupt because the SPI bus is fast. You're not going to be doing a lot of work while it's sending out 1 byte on SPI. There's not a lot of time there, right? So in this case, I think it would probably be reasonable to poll, right? Now, in the case of the accelerometer having data ready, that's happening at a much slower rate. That there's a lot more time that passes waiting for data to be read by the accelerometer than there is waiting for a single byte to be transacted over the SPI bus, right? The SPI bus is running at 4 megahertz. So the amount of time it takes is basically, well, it's 4 clock cycles per bit, and there's 8 bits. So it's basically 32 clock cycles, right? So there's no point in using an interrupt to have it wake you up after 32 cycles.
I would also
right?
point out that the overhead for even using an ISR at all is something like 15 to 20 clock cycles just to handle stack stuff.
Yeah.
Putting everything on the stack and then restoring it afterwards.
Yeah, so it's hardly worth it, right? Yeah, you might have 15 cycles to do something, right? And it's not like you can tell the SPI interface to like send 1,000 bytes. I'll wait. No, it's not that smart. It's not like a DMA engine where you can just tell it, you give it a starting address and a length and have it go in the background. It requires attention after every byte. So, yeah, so you could just wait. But so in other words, what I'm saying is that I wouldn't worry about interrupts for SPI, at least not for SPI. Well, you're the master, so anytime you do an SPI, it has to be initiated by the master. So it's not like you're going to get an SPI message without you knowing about it, right? It's not like SPI messages might come in at any time because you're the master. That's not how it works. So, anyway, yeah, you could poll for that. So that's how you wait for the transmission. Now, once that first transmission happens, you have to do a second transmission to actually. The first transmission just sends what you want to do and the address, and then the second transmission is to do the read or write. So if I'm reading, you could just put a 0 in the SPI data register. Garbage. Because that just makes it go by putting anything in there. You put any byte in there, that'll initiate the SPI transaction, which will pull back the byte that you were trying to read from the slave, right? You guys with me? On the other hand, if you're doing a write, then you would just put the data that you're writing in there, right? And then you would get back a byte from the accelerometer, which would be, I don't know, maybe they put some hidden messages in there or something, but you're supposed to just ignore it. Okay? And then you again wait for the transmission, and then you set the SS to 1 to indicate that you're done. Notice that I left SS 0 after I sent the address, right? You want to do that because that's what's going to tell the peripheral that this is all part of the same transaction, the same operation, SPI operation. Okay, you guys with me? Okay. So for the accelerometer, what are we doing? What are we using this SPI for? The code that we gave you, I think we gave you code that actually reads the who am I. Did we give them that?
I think we just told them to check the who am I
Okay.
once they have some kind of ability to read on the accelerometer.
Okay, so there's a who am I register that is a read-only register, and it has a fixed value in it, so you can use that as kind of a sanity check to see if your connection is up, right? I think it's
It's OX33 is the value that's in there by default.
The register, the address is.
oh yeah, there it is. I have it here. It's address F. It's register 15, and it should come back as 33, right? So I guess they thought, well, 33 is, you'd never see 33 as a random value. So, yes.
You may have said this already. We do provide a header file, lis3dh.h, that has all of the different control register names matched up with what their values should be in like little hashtag defines.
Yeah, so when I say who am I or control reg 1, you can actually, if you include that header file that Philip was just mentioning, you don't have to look up the number of the register. All of these registers are just numbered. How many registers are there? Well, the SPI has is the address of an SPI transaction is 8 bits, and then 2 of those bits are used as flags. So there's only 6 bits, so there's only 64 possible addresses, and I think the accelerometer, uses a subset of those, right?
It's like 50 addresses.
50, yeah. So I get most of, well, that's a lot, but yeah, most of the 64 possible. Okay, so that's a good idea to check that, because if it's not working, you can print a message on the console saying there's something wrong. So this is a way to debug. Once you have that working, you need to initialize the accelerometer, and I think I have all the steps for that here. Philip will correct me if I miss something, but you want to start out, and so you want to start with control register 1. That's where you specify the data rate, sampling rate, right? How fast are we setting that? Do we know? Is it we just 5 kilohertz? Is it like the fastest?
I think we did it pretty slow.
I think
Okay.
for sake of the lab, I think we did a max of either 1 hertz, 10 hertz, or 25
Oh, okay. So yeah, it's super.
You can see the printouts.
Okay, so it's really, you're going to set a slow, you're going to put the low sample rate in there. That's where you specify that. Also, you have to enable all 3 axes, X, Y, and Z. Then control register 3 is where you enable the data ready 1 interrupt. Now, not all of you will be using that necessarily, right? Right? If they don't use the interrupt, they wouldn't necessarily have to enable the data ready 1 interrupt. But if you are using the interrupt, which I recommend you do, then you're going to want to set that up in control register 3. Control register 5 is where you set the interrupt latch bit, which is what keeps the interrupt signal asserted until you have to do a read on the accelerometer to turn it back off. So this is really what solves this problem that I was showing here, which is where you want to synchronize the interrupt with the chip's servicing of the interrupt. You want to make sure that while you're handling the interrupt, you do something that turns it off, that acknowledges the interrupt to the accelerometer, right? So that's the latch setting. Then control register 6, there's the HL active. That, I forget what that is. What's the L active do again? I was just looking at it, and I
Probably check the data sheet because I have it right here. There's one of them that keeps it latched. That's the one. Let's see it.
Yeah, I was just looking at that, and I don't remember what it is now. But those are all the settings. So I wanted to give you a complete, I think this is a complete list of initialization for the chip. All right. So basically, you're going to read this guy, and then you're going to write 1, 2, 3, 4 registers. And you should be set up at that point. And then whatever other initialization you need to do for the, like the interrupt handler.
So the one in Control Reg 6, normally it would pull it active high when there's an interrupt.
Yes.
That inverts it.
Yes, okay, thank you.
It took me forever to figure out over Christmas break. I remember.
Yeah. That references back what I was just talking about. So
The interrupts are tricky with this little guy. If you don't do all three of those things, you're not going to have a good time.
So the presumption here is that when you set up the interrupt, you want to set it to be setting 0, 0, right? Which is the low level of int. This says int 1, but this I captured this from int 1, but this also applies to interrupt 0. I believe it should be the same table. So 0, 0 says that you want to interrupt when the interrupt pin is being pulled low, right? To 0, basically. But in order for the accelerometer to behave that way, you want to set the L active to 1, right? Okay, any questions? Okay, now to use the accelerometer, you are going to be, if you're polling, as opposed to using the interrupt, then you can read the status aux register, which will tell you whether new data is available to be read. Otherwise, you can, if you've got interrupts enabled, you're interrupting to know when new data, you're interrupting to know when the next sample is available. Then in the interrupt handler, you would read X high, X low, Y high, Y low, and Z high, Z low, and those are the actual names of the control registers that contain the 16-bit values for the acceleration, right? So you have, obviously there's 3 axes and each one is 2 bytes each. Make sense? Now, one thing I forgot to put in here is if the interrupt is low, so if you're using interrupts and it drops the interrupt, Philip, does reading status aux, that'll acknowledge the interrupt, right?
There's a particular register you have to read. I think Charles did put it in here in the handout.
Yeah, this stuff should all be in the handout too. I wanted to give you a.
It's int1 source is the register you have to read from, and the data sheet mentions this too.
int1 source. Okay, sorry. So I actually left that out. Let me add that right now.
Because if you don't read from int1 source, the device never knows that you have seen the interrupt.
Is that the name of the register?
Yeah.
Okay.
int1_source.
Okay, assuming interrupt.
Yeah. And
Okay.
then that alerts the accelerometer that you've seen the interrupt, you're good, it can continue collecting data.
All right. So that should make the interrupt pin go high, right? So it'll acknowledge the interrupt. Otherwise, if you don't do that, the interrupt pin will still be pulled down, and so once you return from the interrupt handler, you're immediately going to go back into it again, right? You need a way to acknowledge the interrupt. Okay, so what about CPOL and CFA? Is everyone clear on this? I'm not sure how well I explained this last time. So there's 3 things you have to set up. Anytime you talk to a peripheral through SPI, you have to set up the SPI to match the timing that's expected by that device, and that's through CPOL and CFA. If you read the data sheet for the accelerometer, nowhere does it actually tell you what to set those to. The only way you would know is by looking at the timing diagram. They have a lot of timing diagrams in that data sheet, as they do in a lot of data sheets that you read. So how do we know how to set up CPOL and CFA? Well, you look at the timing diagram, and CPOL basically defines whether the clock is high or low by default, And you can see at the beginning of the timing diagram, the clock is high, right? So C pole should be 1. C fa is a little bit harder to figure out because basically what C fa is it's saying that if C fa is 1, you're going to latch the data, you're going to read the data on the second edge of the clock, right? So the first edge, if C pole is 1, the first edge is the clock dropping. The second edge is the clock going back up. So according to this purple diagram, this purple arrow, when C fa is 1, you're reading the first bit, which in this case is bit 7, because I'm reading the most significant bit first. It's happening on the second edge. You guys with me? So which one are we using? Well, if you look at the sheet, it doesn't actually show. But it does show T setup and T hold. Setup and hold is something that I cover in 611. You probably should have talked about this in 211, but you might not have. Setup and hold is the time before and after you sample data, right? So the moment in time after the setup and before the hold is when you're sampling the data, right? So that's how you know where on this timing diagram it's sampling. And as you can see, that's the second edge of the clock. Guys with me? Also, they call the clock SPC instead of S clock. Don't know why, just confusing. But SPC is what they're calling the clock in the data sheet for the accelerometer. Yes?
After the most significant bit is read from CFA, it samples the data in between, like right after the second edge.
Yeah, well, the idea is that we're assuming that the data is changing on the first edge. And that's shown here. You see that? There's the clock. It's normally high, that's because C pole is 1, right? When it does drop, that's when there's this, you see the cross here? That cross means that now we're going to start changing. We're going to change the data, the bit. It's either going to go up or down. Then 1/2 clock cycle later is when you have the next edge. And by that time, we're expecting that data is stabilized. So it's in a state of flux on the first edge. It should be stabilized by the second edge, right? If CFA was 0, it would mean that this transition would have had to happen earlier, right? Now, why do they have all these options? I don't know. Probably some non-standardization when SPI was first introduced, right? Or maybe it's built in deliberately to give the device manufacturers more flexibility. Who knows? Yeah, I'm not really sure why, but you have to be careful, because if you set those wrong, then you'll be off by you'll be off. If you set CFA wrong, you'll be off by a half cycle. And then as far as the bit order, I just got that. You can see it says MSB first on here. That's pretty obvious. So the bit order should be most significant bit first. You guys with me? So this diagram, just to be clear, this diagram I stole from somewhere on the internet. This is showing the differences between, C pole and CFA. This is kind of a legend. This is a legend, right? This is showing you how to interpret the differences in CPA and C pole. And then this one is from the actual accelerometer data sheet. So I basically use this as a Rosetta Stone to figure out how to set those up based on what the data sheet said in the timing diagram, right? That makes sense? Okay. Okay, so the control register is something you have to set up when you initialize. There's the interrupt enable. That would be only if you're using interrupts. I mentioned to you earlier that probably don't need to, so you'd be setting that to 0 if you didn't do that. The SPI enable has to be turned on. I wrote important here because I forgot to do that when I was writing this, and it took me a while to figure that out. The data order would be 0 for this chip. Master slave select, that's something I also screwed up. I actually screwed that up when I did the demo in class, which made it so I never got it working by the end of class. It was really embarrassing. That should be a 1 because the chip's a master, 328 is a master. Clock polarity should be 1, as I mentioned. CFA should be 1. And the speed, I think the speed can be full speed, right? We doing full speed?
Yeah, I think we were running at 4 megahertz.
Yeah.
It seemed to work just fine.
So if the 0, 0, then 4 megahertz, which is 16 megahertz divided by 4, right? That's much faster than you are, and also much faster than I2C, which I'll get to in a bit here. So SPI is the fastest mechanism. It's the fastest communication mechanism for this chip, as far as I know. Okay, and then there's the status register, which this is the bit you'd pull on, SPIF. Tells you if the SPI transaction is done. There's a write collision flag. I have no idea how that could possibly ever happen because it's a point-to-point connection. Maybe this would be for a multi-slave, like if you have more than one slave. But even then, everything is just a big shift register. I don't know when that would ever get set. And then there's the double SPI speed, and I haven't messed with that. You just set that to 0. Okay, so what would the code look like for writing to the accelerometer? Well, let's say I want to read to address 20, and by the way, 20, I just made that up. I don't even know if there is a register 20. But if there's a register 20, or you don't have to use the number, you could use the name in the header file that Philip mentioned earlier. But basically, I show a variable called read, which is 1 for read, 0 for write, which is just my own thing. I just came up with that on my own. And then multiple is whether you want to do multiple reads or writes. That would obviously be useful for you guys because like when you read the sensor data, you could read all 6 bytes for the sensor as a burst if you want to try that. But I have it set to 0, and then I screwed that up, didn't I? Yep. The read is shifted 7 bits to the left. The multiple is shifted 6 bits to the left. Right, because the read and write flag is the most significant bit of the address. The multiple flag is the next bit, and then you've got the address. So I just ORed those together, right? Make sure you put parentheses around your shifts because in C, shift has very low priority, very low precedence, right? So I think OR has higher precedence, right? So you want to make sure that you put parentheses whenever you do that kind of expression. So that would be a way that you would set it up to read, turn off multiple access, and then set the address in the data register in 3 lines of code. And as soon as you write that data register, assuming you've dropped the slave select line before that, it'll initiate the transfer, right? Well, at least the address, and then you have to do it again for the data, right? So this is like a little snippet of code, but that is really just part of the overall thing, which is the basically step 2 on here. Right? Make sense? So you probably want to write a function that does this, right? It's probably best to write a generic function that basically does all these steps. So you call the function once and then it does a complete read or write, right?
Initialization function that will just do all that at once.
Well, this part, you initialize this stuff, but then you want to have like a read Excel function or write Excel, or you can have an access Excel, and then you can specify in the parameters whether you want to read or write. Or you could write a special one for reading the accelerometer, since that's going to be a burst potentially. So it's up to you how you want to set it up. We're going to, but I think it's best to have a function for that. Okay. As opposed to just putting everything like in main. Okay. Okay, then I have the relevant registers. I copy these from my earlier talk. These have the numbers, but you don't necessarily have to know that, except in this case you do, because if you do a burst transaction, the addresses have to be consecutive. So I think they are, right? 28, 29, 20A, 20B, 20C, 20D, right. So it's good to know the addresses for these registers because you can confirm that they are consecutive numbers. The other ones, it doesn't really matter because I think the only time it makes sense to do a burst is for the sensor data. Then there's who am I, the status aux register, which you'd use for polling because that one has a 321DA, 1, 2, and 3 access new data available. Tells you if new data is available. Right, so if you were polling as opposed to using an interrupt, you can check that bit to know if it's ready. Is that right, guys? That's right, right? This bit, the status aux, the 321DA is going to be a good bit to check if you're polling as opposed to using the interrupt, right?
In our reference example that we have for doing polling, I am 99% sure that's the bit we check.
Okay. Okay, and if you're doing interrupts, then you would want to acknowledge the interrupt not through that, but through
One source, I think.
yeah, int one source. Yep.
Yeah.
Yep.
Simply reading int one source is all it needs. It
Yep.
will unlatch the interrupt.
Does that make sense? You guys follow that? So if you read the int one source register on the accelerometer, what's it telling you? Well, it doesn't matter. You just ignore whatever it is. But by reading it is what acknowledges the interrupt. It's the way that your code tells the accelerometer that, okay, I understand data is available and I've consumed it, so now stop trying to interrupt me, right? Sometimes just reading a register has side effects. That's a side effect of reading the register. You don't necessarily care what's in there, or you might want to look at what's in there, but I think in general, if the data is ready, all three axes are ready. Okay, any questions about that stuff? Okay, so hopefully between that kind of review of stuff that I kind of blew past before, and also the handout and help that you've got in lab, hopefully that's enough information to finish up lab 2. I think the handout has basically a lot of the same stuff I had in here, kind of step-by-step methods to do stuff,
the
right?
LIS3DH handout has basically that entire sequence of things you have to do to get interrupts going. It has a little section on that. I'm about to add a thing on how to convert the output values you get from the LIS3 into floating point numbers that'll make sense. Because for those of you that got your accelerometer reads working in lab last Friday or last Wednesday, you probably noted that you were getting all these weird power of 2 numbers that don't make any sense. By default, the accelerometer is just spitting out integers. You have to actually run them through a little conversion equation to get things like 9.8 meters per second, for gravity on the z-axis and stuff. So there will be a little formula in the handout that will walk you through how to do the conversion. It's pretty simple. It's just finding the right constant to divide by that's tricky.
Okay, those handouts. But I hope everyone is aware of this. But the handouts are all somewhere here on the Dropbox. Actually, they're not on that page. They're down here. Yeah. So the handouts are listed here. The code that I cover when I write code in the class is for the demos is also linked here. And also, by the way, I've got I don't know if I think most of you probably know this, but I've also got the link to the lecture, the recorded lectures on here. I've got them. I've actually become gotten a little obsessed about that now, trying to make those. Yeah.
I appreciate that.
What's that?
Solid thumbnails.
Oh yeah, thank you, thank you. Yeah, I do in the thumbnails. I got I'm trying to do the camera angles and all that stuff. So, plus I clean up the sound, the audio, which is I think the most important part, so you can understand what I'm saying. It's not all echoey or noisy. Okay, so let's move on to the next topic. We're going to cover I2C. I2C is the third interface technology supported by, yes?
So in SPI, when you have a slave select, if you have multiple peripherals and it just acts as a big shift register, why do you have to select a specific peripheral?
Well, it depends on how you set it up. If you fan out the slave, if you fan out the MOSI, right? So you see, I don't have it in. Actually, let me bring it up here. I think I had that in lecture 2.
Is that kind of what I2C deals with in a sense?
Yeah, sort of. So you can, if you've got it in this configuration, if you've got it in this configuration, you would have a separate slave select for each slave, right? And so you would select, you'd select a slave, and then
Okay, so you have multiple slave select pins. It's not one that you try and distribute them.
well, in this case, but see, this is kind of strange because the master in slave out. There's a separate, in this case, there's a separate master in slave out for each slave. And these are actually shown as kind of just shorting into one another. You see that? So this would be kind of dangerous because you'd have to make sure that only one of these guys was actually driving the master in slave out. The other ones would have to be tri-stating it, meaning like disconnecting it from the driver, right? So it would have to be floating on all these guys because you wouldn't want to have this guy and this guy trying to fight each other for that master in slave out, because that could cause issues. And I'm going to talk about that in just a minute when I get to I2C. So this is a little dangerous, I think, because you'd have to make sure that these are well behaved. In this case, there's only one slave select, and you treat all these things as one giant slave, and you just shift all the way through. So, but yeah, the slave select I think was designed with this sort of configuration in mind, where the slave select is essentially telling which one of these slaves to connect its MISO. And it would have to be mutually exclusive. You can only have one of them. So you'd only have one slave select active, and that would be the way that you'd prevent double driving MISO. Right? And I think that's probably why, because remember I said when you drop slave select in the accelerometer case, it's almost redundant. Like, who cares? It doesn't really do much except demark, a one register transaction. Since you have to do multiple SPI shifts, it just shows you that you're doing an operations part of a group of transactions to do a read or write, right? But other than that, it doesn't really do much. But in this case, it would be necessary to avoid double driving MISO. MOSI is not a problem because you're just fanning MOSI out to all of them. They all see the same MOSI. But MISO is the issue there. Yes?
Before we move on to I2C, for part B, for with the LEDs, we have to do the LEDs at a certain efficiency, not lit up all the way.
Mm-hmm.
How do you do that? Is that it's when you were doing the breathing last time, is that
yes.
That's a lower efficiency there? Or?
Yeah, you're using pulse width modulation to control that. So what I showed last time, there was a little bit of a miscommunication. Last time I showed how to do hardware PWM, and the problem I was solving last lecture was you only have there's 6 hardware PWMs, and I wanted to show how you could use one hardware PWM to control the brightness of multiple LEDs independently from one another. So I did this time division multiplexing trick. Right? In this lab, you don't have to do that. You don't have to use hardware PWM. You can use software PWM, meaning that you use the wait function. So you basically set the pin high, and you just use a _delay _US function to delay it to control how long it's high versus low. Right? So there's 2 delays.
30% efficiency. It's only on for 30% of the time that it should have as a full cycle.
Right. Right, yeah, so you would say say your period was a millisecond, right? So 30% would be you'd set it high and you delay for 300 microseconds, and then you would set it low and delay for 700 microseconds, and then that would be part of a loop. And that should give it the appearance of a 30% brightness level.
Okay.
Although, as I described last time, it's not really true because it's not a linear relationship between the PWM duty cycle and the brightness, because at the bottom, like a really low PWM values, it's basically off. And once you get beyond like 70%, I think it's at full brightness. There's a linear region sort of in the middle, but I don't think we're requiring you to work all that out. You can just assume that it's 0% to 100%,
Okay.
right, on the PWM. Does that answer your question?
Yeah, I was just wondering how
Yeah.
you light up the light bulb like 30%.
Yeah, it's like you just essentially send an analog value, but it's the fake PWM analog value. The other issue with that, by the way, was I think the problem there was, yes, here was the problem. You need 6 bulbs, right? 6 LEDs, and there actually are 6 hardware PWMs because there's 2 per counter and there's 3 counters. But the problem is this one, OC2A, which is the first PWM output of counter 2, shares the same pin as MOSI, which means that you cannot talk to the accelerometer over SPI and get access to all 6 hardware PWMs. That's the reason why we're having you do software. Does that make sense? So I was trying to fix that. By the time I figured out a workaround of that, which is the hardware multiplexing, we had already put the lab together for software PWM. Does that make sense? Okay, so, okay. Oh, sorry, that's lecture 2. Okay. Okay, so I2C. So I2C is about as commonly used as SPI in embedded systems. They both sort of persist because they each has advantages and disadvantages over the other. SPI is single master, which means that only one device can initiate transactions on the bus. Even if you have multiple slaves, even if you have a multiple slave setup, you still just have the one master, so you can't have a slave initiate contact with another endpoint. So I2C is multiple master, which is it allows anyone on the bus to take mastership, and it only requires 2 wires as opposed to 4. The wires are called SDA and SCL. SDA is short for serial data, and SCL is short for serial clock. So one's data, one's clock. There's no slave select because it's self-arbitrating. You basically have a shared connection, and whoever wants to have mastership tries to take control over those pins. So it's self-arbitrating. And obviously it's not shift register based. It's half duplex. So only whoever's master can send bits. But unlike SPI, where as you're sending bits, you're also receiving bits at the same time, you lose that capability. So that's why it's only 2 pins. You don't need the slave select because it's self-arbitrating, and you lose MISO, because it's half duplex. So less pins, but half duplex. The other nice thing about I2C is that it has an acknowledgement mechanism. So if there's any kind of an error, there's a way for the recipient, whoever the master is talking to, can signal an error and initiate a retransmission. Whereas with SPI, if there's an error, there's no way to indicate that with SPI. There's that right collision flag that we found in the SPI status register, and I don't know how that's detected, but in general, SPI is not very robust against errors. Right? Okay. One thing that's a little confusing is that Atmel calls I2C the two-wire interface, TWI, even though the rest of the world calls it I2C. Don't know why, but just keep in mind that TWI and I2C are the same thing. Okay, so why is I2C multi-master and SPI isn't? Why is that? Well, this SPI is a push-pull, uses a push-pull interface. So this is something else that I normally cover in 611, but when you have a driver, when I say driver, this is the actual circuit that sets an output bit to 1 or 0, driver, right? A push-pull style driver would be like having sort of like having an inverter that sets the value. That value is connected to both a P-type and an N-type transistor. The P-type transistor is used to pull up, meaning that when I want to send a 1, I activate the P-type transistor and I deactivate the N-type transistor, and that makes the resistance value here between these two terminals very low, and it makes the resistance here very high. So it effectively turns on this switch and turns off that switch. So it takes the wire and it pulls it up to VDD. It creates a low impedance path between the output and VDD. Pulls it up. Or pushes up. Likewise, 0 is I pull it down, I do the reverse. So that's why they call this CMOS. It's complementary in the sense that only one of these is activated at a time. You're either pulling up or pulling down, right? And then that signal would then be connected to an input. And what's the difference between an input and an output? In CMOS, an output, you know something's an output because it's connected to the sources or drains of the transistors. Inputs are things that are connected to the gates of the transistors, which is not, this is actually the input here. You guys with me? Okay, well here's the problem. If you have a shared bus and you have two drivers connected their outputs to the same physical wire, as I'm showing here. So these guys are mirror images of one another. So the input is here, the input here is here, but the output is, the outputs are connected together. So they're both outputting to each other's output. So, and this would make sense if this were a shared bus, because I want both of these guys to be able to write to this bus, right? The problem is that if this guy is pulling up, like if this N transistor, this P transistor, sorry, is on, and that N transistor is on, they're fighting each other, right? This guy's trying to set the bus to 1, and this guy's trying to set the bus to 0. The problem you have there is that creates a short circuit, because you have a low impedance. See, in CMOS technology, you always assume that there's always a low impedance path to VDD and a high impedance path to ground, or the other way around. But if these two guys are both fighting for this bus, this guy's pulling up, this guy's pulling down, you end up with a low impedance path from VDD to ground, right? So basically you're going to have current flowing down through here and then down through here, right? And MOSFET transistors are so good when they're on. Their on impedance is so low that in this case you will burn up these chips. You will physically damage these chips because you'll have too much current flowing through this guy and that guy. It'll generate a lot of heat and it'll fry your chips, right? This is the same thing that I just mentioned with the multi-slave configuration of SPI, right? The reason why SPI has the slave select is so you want to make sure that only one of the mesos are active, right? Otherwise you would run into that same problem, okay? However, there's another option here. We can use something called an open drain. Open drain is when you don't use CMOS. Instead, you have a pull down NMOS resistor that can both be attached to a shared bus. And then you can have a resistor up to VDD, right? So that way, if these guys are both off, then this bus will be pulled high by this resistor, right? Now you have to be careful how you set up this resistor, because if the value is too high, it may drop the voltage here. If the value is too low, you may get too much current when you have it on, when you have the NMOS on. But the point is that you can have this shared bus now, because you can turn these both on, and this resistor will guarantee that you don't sink too much current. Does that make sense? So with I2C, the way that it's set up is that all of the devices that are on the bus, they share both the SDA and the SCL lines, but both of those guys have pull-up resistors, right, to allow them to be shared. Now, where are these pull-up resistors? Charles had a hard time figuring out if you were supposed to put these pull-up resistors in yourself, like add them to the breadboard, or if they were provided internally on the 328.
I think we decided that you could have to do it yourself.
Well, I think if you look at the DDR register, and I think there's an option to turn on a pull-up resistor.
No, well, that would have saved some trouble.
So I think you can turn it on if you set up the control, the DDR and port, right? If something is an input, you set the DDR to 0, but then you can set the port for that input to 1 or 0, which defines whether or not it has the internal pull-up activated. But anyway, that's basically the idea. But here's where it gets really neat. Oh, and this is another picture showing kind of the same thing, right? But here's where things get really neat. This is the part I like. So how do you decide whether, there's who do you decide who gets to arbitrate, who gets control of the bus, who gets mastership? How is it self-arbitrating? Well, first of all, let me just get right into it. So you've got the data and you've got the clock, right? So as a general rule, the data line, which is SDA, data is only, wait, I have that right? Hold on a second. Let me look at the timing diagram, make sure I don't get this wrong. So here's the timing diagram. Notice that the data is changing. It changes whenever there's a transition here, right? But notice that every time the data changes, which is where these crosses are, the clock is low. And while the data is stabilized, the clock goes high and low, right? Make sense? So this is not acting as though it's an edge-triggered clock. This is a level-sensitive type of latch system where the data gets consumed when the clock is high, and you're expecting that there should be a rising and a falling edge of the clock for each bit that you send. Make sense? So what's the significance of that? Well, if you violate that rule and you change the clock, you change the data while the clock is high, which happens right here. See, the clock is high and the data drops, right? That means something special. That means start. That's a start signal, right? Likewise, look at the end here where clock is low and the data changes here. Sorry, no, I got that wrong. It's actually here because these are two transactions at the end. The data, the clock is high. Sorry, the clock is high, and I change the data. So the same thing happens here. Clock is high, data changes. Clock is high, data changes. You should never do that if you're sending data, because that is how you signal a start and a stop signal. Make sense? So when clock is high, if you drop the data, that's a start or a stop. If it's a stop if you've already started. You guys with me? Once you start or stop, then you just send data, but sending data requires that the data only changes when the clock is low. So the data changes, then the clock pulses. So the bits are conveyed through pulses of the clock, as opposed to looking at edges as we did with SPI. In this case, we're looking at pulses. One clock pulse, up and down, is the way that you send a bit. And you have to be careful that the data line only changes when the clock is low. Yes?
Does this almost synchronize it in a sense that the last lab, a lot of us had baud rate issues where we would send and receive
different rates. Yeah. So it's synchronous, just like SPI. It's synchronous. You have a clock. The difference is that it's not an edge clock. It's a level clock. It's a pulse. It's a pulsing clock, as opposed to a clock where you're dealing with the edges. So with SPI, we had CFA. CFA was all about what edge. What edge does the data get sampled on? Is it the rising or the falling edge? And together with the C-pole, you can figure out whether the data is sampled on the rising edge or the falling edge. Here, it has nothing to do with edges. This is pulses.
So if you pulse too quickly though before data changed, that would still run into the same issue of misreading bits.
No, if you change the data, if you didn't pulse fast enough, it would be an issue, right? Okay. But you need to be able to. But that's okay, because whoever's sending the data is in control of the clock. So that's the other thing that's happening here too, is that there's a handoff process where when I take mastership of the bus, obviously I have to send an address, whether I'm reading or writing, right? So when I'm master, I can read or write. But before I do either one of those, I have to send the address. At which point I control the clock, because I have to pulse the clock to send the address. But whoever's at the other end, who's the recipient of my read, if it's a read, he'll have to then send a response back to me, at which point he will be in control of the clock, right? So there's going to be a handoff in ownership of the clock, right? So also I mentioned there's an acknowledgement. So the I2C is similar to the SPI, where the address and the read or write flag are part of the same introductory bit sequence, right? But then there's an acknowledgement flag. This one's pretty cool. So after I send the address and the acknowledgement, whoever's at the other side can acknowledge that it received that byte. And every byte is acknowledged, by the way. So whoever is sending the byte, the recipient of that byte is going to have to acknowledge, right? And the acknowledgement is, the acknowledgement happens after you send, so you're going to send 7 address bits plus the read write, so that there's 8 bits, and then the host is going to have to respond by pulling SDA low if it's an acknowledgement, right? Data. Well, think about that. That's kind of crazy, though. Think about that. I just got done sending bits to the other side of the link, right, with data. As soon as I get done with that, after eight bits, it will then, the endpoint is going to have to then also pull that down to acknowledge. So there's a very quick handoff here between the sender and the receiver. You guys with me? Make sense? So then obviously, like I mentioned, if it's a read, then the other side is going to have to do his pulsing and send the data back, right? And then I'll have to acknowledge that, right? Or if it's a write, then whoever initiated it will have to send the data that he wants to write. Again, it's all byte-based, so the addresses are a byte. Well, the address plus the read or write flag is a byte, and the data is a byte. Or sent in bytes, I should say. And every byte is acknowledged. Any questions? Okay. Yeah. So I tried to put these steps down like I did before for SPI. So pull SDA low with the clock high, which is usually a no-no, except unless you're doing a control sequence. So this is a start sequence. Then you pull the clock low. At that point, I'm going to basically hold the clock low, except for when I pulse it, right? So then I start pulsing it, starting with address bit 6, because there's going to be 7 address bits, 6 to 0, starting with the most significant bit. Then I repeat that until I get to read write, and then I send that. And then I'm going to pulse the clock here. So whoever's initiating the transaction does this final pulse and is looking for the other end for them to acknowledge or not acknowledge. If they acknowledge that they receive the byte okay, they'll pull SDA low. So I am driving SDA and SCL until this, at the end, when we come to the acknowledgement, at which point the other side of the link is going to take control over SDA and I will pulse SCL. Okay, and that'll be the acknowledgement. If he holds it high, then that means that's a NAC, that's a not acknowledged. Make sense? Okay, now here's where things get kind of crazy. I only got a few minutes left, so I'll just kind of tease this. Doing TWI on the 328 is a lot more involved from the software perspective than SPI is, because I2C is slower than SPI in terms of data rate, but it's also a lot more robust. So it seems to me, I don't know the whole history, but from having used them both, I2C comes off as a protocol you'd use in less reliable, less ideal situations, like maybe longer wires or more noisy environments, that kind of stuff. Because there's this acknowledgement mechanism where you can, the transmitter can detect errors. And as it turns out, the hardware on the 328 is set up with this in mind. So every time you initiate something on the TWI interface, you're constantly checking for the status. You have to check the status every time. You send the address, you have to check no, actually, you send the start sequence, the start signal, which is dropping the data when clock is still high, right? Then you have to check to see if, did it work okay? Because it might not have worked, because you might have two hosts trying to simultaneously claim the bus, right? There may be a collision, right? Because it's multiple masters, right? Potentially, right? So you have to check to see if you successfully initiated the start sequence. Then you send the address. Then you have to check to see if the address went through okay, to see if the acknowledgement worked okay. Then you send the data, or you receive the data. Then you have to check again. Then you do the stop sequence, and then you have to check again. So just doing one read operation of 1 byte requires you to check status 4 times on the 328. Right? It's a lot more code involved. And also, these are all the different statuses just for the transmitter mode. Look at this table. It's crazy. These are all the different outcomes the TWI interface could come to based on what you're trying to do, right? Whether it's trying to do a start or address data or stop. That's for the transmitter mode, and then the receiver mode has all these other status codes. So it's a lot more effort, even when you have the hardware I2C interface. But it's the good news though is it's a more robust interface. You have a better idea what's going on. So why would you use one or the other? Well, certain peripherals only support SPI, certain only support I2C. Some, like the accelerometer, I think support both. Right? You have the option. Now, the other reason why you'd want to use one or the other is, in our case, we only have one SPI and one I2C, so we may want to use both just so we could talk to more peripherals. So, in fact, that's, I think, what we're going to do once we get the screen hooked up with the accelerometer. Any questions? Okay, good. All right, well, that's all the time I got.